So I'm going to start. I'm Nicoletta Prencipe. I'm a postdoctoral researcher in the perception engineering group here. And we're going to do the second half, like the middle half of this class with me. So I'm going to tell you a little bit more about this. And yeah, so I suppose I should introduce myself. So I'm a postdoc, and before I was a PhD student in France. And I did a PhD in applied mathematics, and before I have a degree in pure mathematics. So, and now I'm a postdoc here, so I'm doing things that are related to math and perception overall. And if you want to hear more about that, also about, I don't know, master thesis projects and stuff like that, it's possible. So feel free to catch up. Do you really hear me, everyone in the room? Like, or not really? Should I like speak louder? Okay, good. And yeah, so I wanted to hear how many of you are PhD students here. And also a little bit, I don't know, I was curious about your background. So what did you start, like what are you studying now, or what did you study before to like enroll to these classes? So maybe we can like do a round of introduction. I don't know if you feel comfortable with it.
Vadim already did that last week.
Yeah, so I just take the information from Vadim. And I don't want to know what they do. Okay. But yeah, so I'm just gonna tell you some information that probably you already heard, because some people like emailed me about where is this course on the PEPI on Moodle. This is the ID code, so you can find it through that. So the slides of the whole week, I will update them on Friday. So we see each other twice in the week, but you will have all the materials on Fridays, because some things are like need to be put together. And also the exercises should be returned on Fridays and are published on Fridays from the previous week. So I think this Friday you have exercises from last week to return. You return them on Moodle and on one single PDF file containing the number of the week, your name, and your surname. Also, I have a question. Is there anyone who attended the class last year?
There was one guy.
Yeah, I don't remember. Okay, so another thing, other info, whatever question you have, feel free to email, or like there's much more stuff on the Moodle. So whatever question you might have, probably it has been already answered there. Also, there is a poll where we are asking you whether it's okay for you to switch, not from this week, but from the next one, the class, instead of doing class on Friday, we do class on Wednesday, and we do exercise session on Friday instead. So there's a poll, you go vote. If you don't care, don't do what you want. But yeah, there is like, your opinion is taken into account in this decision-making process.
I'm not sure there's a poll yet, but
they will be today. Yes. Yeah. And so this is the program of what I'm gonna do. So it's not the program of the whole course. This is just what you're gonna do with me. Okay, the dates are like Mondays and Fridays, but let's see if we switch Mondays and Wednesdays. So I'm gonna do week 2, 3, 4, and half of week 5. We are in week 2, and we're gonna do McCulloch-Pitts units today, and next time we're gonna do perceptrons. Other topics that we're gonna see are Hopfield networks, reinforcement learning, and ICA. So I'm gonna just do half of ICA. A little bit of the maths that is needed in all this is, in the last one is probability theory, some of that. So we're gonna do some recap in the beginning of every lesson of the maths that is needed. For today's lesson in particular is logic. So, but we're gonna do everything, like it's not crazy stuff. So we're gonna do everything from scratch. So probably if you come from computer science, logic is the least scary one. I know. And we use some stuff from graphs, but not that much, I'm gonna say. Hopfield networks are like, with a little bit of like cute graphs to play with. And in reinforcement learning, there is gonna be, I think, some probability still, but like, yeah, the topic is more about, I don't know, you have a robot that works on a plane and like it gets hitting the walls, and like gets punished if he hits the wall, and gets rewarded if he reaches like a treasure or something. So this is the kind of problem that will be treated in a reinforcement learning class. Yeah, that's more or less it. But basically, all the maths tools that are needed will be like re-explained. So don't be afraid of that. Yeah, and like all these topics, like one could do like an entire course on each of those. So we have to like to keep in mind that all these like weeks are just an introduction to these fields. So if you're getting interested in that, there's like always the option of going deeper and like getting more knowledge on all of this stuff. Are there any questions so far? Nope. So I go on. Are there any questions online? Nope. Yes. Okay. So all the materials from this week is from Raja's book. That is like, we have a link on the Moodle page, and it's like available online, so you can find it. And so if you want a book to look at, the topics are covered in this book. So I'm gonna talk about logic. I think it's not very crazy stuff. So, but let's start. You probably know about these symbols. You've already seen these symbols before, right? How many of you have never seen this stuff before? Okay. So yeah, essentially one, like probably you have seen this as logical connectives. So you have two variables that can be into 0 and 1, and you do the and the or, etc., and the negation. And you can, sometimes people put an order of importance in these things, like when you do operations in algebra and you do multiplication before sum and stuff like that. You can do like an order of importance also with those. And the order is the one that I wrote. So we do before negation, and then you do and then you do or. And so you don't have to put parentheses. But if you want, we can put parentheses as well. All these things can be written using truth tables. I hope you've already seen those. How many of you have seen truth tables? Okay, so maybe I'm gonna just write them. And if it's too easy, I don't care.
I will change it to the camera so that people can see
Yeah.
what you're writing.
Yeah. So one can write, I don't know, if you have two variables, x1 and x2, do you see? Should I write bigger? Bigger, do you see?
Definitely bigger.
Okay.
Especially for the online folks.
And they can have values 1 and 0, so you can put all the possible options.
Yeah, that's better.
And so, like those are all the possible combinations of the values that x1 and x2 can take, because they have said that they have values in 0 and 1. Sometimes we write this, I don't know, this notation can be weird sometimes, I don't know. 0, 1 times 0, 1 Cartesian product is the set of all these couples. But sometimes we write this. It's not a crazy notation, but it's a notation, so just be aware of that. And yeah. So one can write negation, for example, and x1, meaning that you switch all the ones to 0 and all the zeros to 1. So you have this. And one can write x1 and x2. It means you want both x1 and x2 to be true. So you just have this, and then 0, 0. And then you can have this. Or is notated with V because it comes from Latin. So vel is or in Latin, so that's why people put V. It's not really a fun fact, but it's a fact. Or you have to have this, right? Did I make a mistake so far? Yes or no are the options. Okay, let's move. So with this, you can do combinations, like those are the operations, and you can do whatever combination of these you like. And yeah, there is many things that could be said here, but I'm gonna stop at this point. So
What do you call that?
what?
That notation. X1, the first notation.
This one.
No, the third.
The third?
That's a not.
Negation, not.
Not.
Yes. So, I suppose I did. Oh, did I do wrong? No,
That's fine.
so this can be written as operation between variables, but the way we're gonna see them in this class, like I did this recap. Oh,
You can continue talking.
so yeah, so the way we're gonna see them in this class is this as logical functions. What does this even mean? That, for example, the OR here. I'm gonna say that OR is a function that goes from 0, 1 squared. So it takes x1 and x2. Cartesian. So it takes like all these couples and send them to 0 and 1 squared instead of n. So, and these functions can be expressed using the same tables because the tables tells you the image of each couple in this case. So you specify the whole function just by saying what is the image of each of the point in the domain. And you can do it with OR, you can do it with everything. Is this weird or is it okay? We can specify all the functions that are like called logical functions and or Boolean functions in this way, and you can take it by the power of n, meaning that you have x1, xn in the domain. A vector called x1, xn, and the image, we call it y. So the first question might be, is 0, 1 at the power of n a set which has a finite number of elements or infinite? Oh, someone wrote. Are there a fine, like, is this set? Well, what is the, like, is does it contain an infinite number of elements or just a finite number of elements? Yes. And how many? N? No. Someone else. 2. Like this? So, sorry, can you repeat? Yes. Why is it 2 to the power of n? Yes. So if you have, I don't know, imagine that you have a bar with n lights that you can turn on or off. Those are n. And lights that I can turn on or off, and interrupters. Okay. For this, I can have 2 ways of doing it, and the other one I have 2 ways, etc. So I have 2 n times. So 2 to the power of n. So how about f? Does f, so the set of all possible functions that go from this to 0 and 1. This is a bit harder of a question, right? It's okay. Does it contain like f? So this f, not f straight, f like this. The set of all the functions that go from 0, 1, n to 0, n, is this an infinite set, or does it contain a finite number of elements? Do you agree? No, it's finite. So how many? This takes some time actually, like what? No. It's more than this. This is a bigger set because you have all the options where to send those. So I suggest you to use this idea and to repeat it. It takes some time, but it's okay. Like sorry? Yes. Yes. Why? Yeah. Another way is to reuse this. So you can say that I told you that if I have a set of n elements and I can turn on or off each of these lights, I can say that I have a set of m elements. That is the number of points in the domain. So I call this m. To each point in the domain of this function, I can choose whether to send it to 0 or 1. So I have two options. So the cardinality of f is to the power of m, but m is equal to 2 at the power of n. Because m is just this. So like I forget about calculating this basically. And I say I have big M elements in the domain, and I have to choose whether to send them. So the image of these elements is 0, 1. So I have like the same problem I had before, but reiterated. So that's why it's to the power of n, to the power of 2n. Do you hate these exercises? Yes, okay. This is the last one we're gonna do of this stuff then. Does someone like this type of exercise? It's okay to hate them. But this one was a bit of a harder choice. Like this last one. So this is an example. So imagine that we have 0, 1 at the power of 3. So we have three variables, x1, x2, x3. And this cube is the set of all the possible triplets, x1, x2, x3. Imagine that I have a, okay, let's do it. X3, then I can do this. Etc. Okay, so I can picture whatever is going on by the vertex of this cube. And before we had 2 to the power of n, and now it's 2 to the power of 3. So you can picture whatever types of, like the domain of these like logical functions is the vertex of this cube, just the vertex, not the points in between. We're gonna use that maybe later or maybe next time. So that's why I showed the picture. So all this is because we want to do McCulloch-Pitts units. Probably Vadim told you a little bit of fun facts about these two guys that invented those in the 40s. They published this paper. One was a neuroscientist, the one on the right, and the other was a guy who did logic, like Vadim. So they were like putting together all they did, and they invented these types of neurons, let's say. So all the class today is going to be about some ideas that those guys developed. And the purpose in the end is that we're going to be able to express the all the logical functions using the things these guys did. And as you will see, because last week, did you see like the usual networks, right? The ones with the weights and like the nodes, etc. Here, all the weights are 1. So there is no weights. Like if your weight is 1, you're just letting the thing pass. But so the idea of what they invented was to create some kind of like new, let's call it unit, just one neuron that does a similar thing, but that is similar to the biological paradigm. So you have different type of ways of connecting the inputs to the neuron itself. So, and also you have seen functions as graphs last time, right? Oh, you have that on the notes, so you have seen it. So this is a picture of a McCulloch-Pitts unit, and as you can see, there is just like inputs and output. We call the inputs x1, xn. In this case, it's x1, x2, and you have an output that we call y. There is also a threshold. What does it mean? This theta. Oh, let's forget this. Okay. There is a threshold function that is posed on the neuron. So before that, why did I put a circle and an arrow that are different? So in McCulloch-Pitts units, as I was already saying, the edges of the graph have weights equal to 1, so they don't have weights. They are directed, means they go from like, oh God, right to left. They go in one direction, like usual networks. Why am I saying that? Because when we're going to see Upfield networks, the thing is not directed, so it goes all over the place. It's not like a network as you see. I don't know if you've ever seen like pictures of neural network that go like a flow in one direction, etc. Not all the models that have been invented in this domain do that, but this does. So it goes in one direction. You go from the input to the output, and that's all you want to do. Are directed and weighted? I mean, you can say weighted with weight 1. And they can be of 2 types. We call them excitatory if they are an actual arrow, or we call them inhibitory if they have a circle. So I'm going to say what they do in just 1 second. Like there's a difference in between the way they transmit the input. Is everything okay so far? Yes? No? Okay. Are there any questions? Oh, someone replied infinite. Okay. No. Okay. Yeah. So I said that there is a threshold, and the threshold is this. So what does it mean? So if I have an input, if the input is strong enough, it will pass, and if it's not, it won't pass. So there is a threshold function that we could have, like it's a Heaviside step function, because this guy used those, I don't know. But basically, if the stimulus is greater, so if the input is greater than theta, it will output 1. Otherwise, it will output 0, greater or equal. So, yeah, this is a type of activation functions. I think you already seen different types, like the sigmoid, the other weirder things. But this is like the simplest one that we use in this network. So, if the input is big enough, it will pass. Otherwise, it won't. Are there any questions on this? Break. No? Do you hear me right? Or should I speak louder? All right. Okay. Yes. So I'm going to tell you the difference between excitatory and inhibitory edges. An excitatory edge is just an edge like the one you're used to. So if I have an input, let me write here, maybe it's better.
Right there, I'm gonna clean this.
So if I have an input x1, the excitatory edge will just bring x1. It doesn't care. But what does the inhibitory edge does is that inhibits the, okay, yes, so basically if x1 is equal to 0, so sorry, to 1, it will bring 1, and if it's 0, it will bring 0. So it does nothing. What does the inhibitory edge do is, if I have this, oh God, no, this. So if it gets 1, it means that it will inhibit the neuron. So it's turning off all the machines. So the output of everything, so the y, will be 0. So basically this thing turns off the neuron. And whenever it's 0, it does like the excitatory edge. So it just passes 0. But this literally shuts down all the thing. So that's the difference between the two. How are we gonna? But yeah. So
Yeah, a bit
Yeah,
bigger, and
it's
maybe
fine.
use black.
yeah,
Still black. Yeah, there's black here. You can
I
use
can-
this.
I can write on this one. It's fine.
Okay.
But yeah, so basically, if you have this is the excitatory type that does 0 and brings 0, and if it gets 1, it will output 1. And this other type, if it gets 1, it shuts down everything. So it shuts down. And if it gets 0, it just will pass 0 as the other one. So there is 2 types. How these machines work. So imagine that you have one of these, like the one before. I'm gonna probably make an example. So yeah. So I have x1 and x2, and I put 2 excitatory edges. And I put theta equal to 1. What this machine does is, okay, yeah. Takes the inputs of both of these. So we can write a truth table again. So we can write x1, x2. It checks whether there is any inhibitory edge, because the inhibitory edges can shut down the machine. So since there is none, I go to the second step. The second step is I take all the edges and I do the sum. So I have 2, 1, 1, 0. Then I put the sum through the threshold. So y is h of theta, because I said that there is the activation function of the sum in this case. So what do I get? 1, 1, 1, and 0, right? Because this is bigger than 1, this is bigger than 1, and this is bigger than 1. So they all pass except for this last one that is 0. So basically what I did was the truth table of something that I showed before. That was what? 4. So the idea is that can we do all the logical function using these machines? Let's see. Yeah, so do you wanna try to do one with the, what if I put 2? Yes.
So is it always an or function that is being done between the excitatory edges and the inhibitory edges? It's always an or function for the McCulloch-Pitts unit.
Sorry, can you repeat the question?
Is it always an or function? An or operator that works on the 2 nodes, that's the 2 edges, which is excitatory and inhibitory edges. Like the equation we just did now.
Yes.
It's an or function.
Yes.
Either this or this. So is it always an or function? Or
No.
There's a case where we have to use an add, just that.
Like in this case, like the outcome of the function is an OR function. But what if I put theta equal to 2? Do I get an OR?
Maybe you can show the function of the h.
So if I put theta equal to 2, what does it happen? Like here. My activation function is different because my theta is different, right? So if I put theta equal to 2, these values will be different because this theta is different, right?
Okay, so that means that it's always an or function, that we have the threshold inside of the inside of theta. If we say theta is equals to 1 now, then that means everything will turn out to be, we would have like 0, 1, 1, 0. Is that correct?
Nico, can I try to explain? Because I get what he's asking.
It is an odd function when theta is equal to 1, and when you have this type of edges. That is the case that is equal to 4. If you change this, might not be the same. But it's not true that there is only one McCulloch-Pitts units that can do a logical. There is not one-to-one correspondence. We're going to see other examples, so maybe it will be clearer later, but we can talk. Yes. So what is going on if I put theta equal to 2? So what did I get? Yes. So those are the ones that I just showed. And yes. So the question is, can we do any logical functions using this type of machines? It means also that I can put more inputs, and I can change the thetas, and I can put the circles. So all the types of freedom to like with the concepts that we introduced before, how much can we do? Can we cover all the set of logical functions? This is like the questions that we're going to face until the end of this class. So are there any other questions? Are there any other questions? Yes, you take the sum because you take the sum of whenever you don't have anything that shuts your machine down, you take the sums of all inputs. And even if the thing that shuts down is off, like it's 0, as 0 input, you sum the 0. So you are summing everything in the end. But if this is on, so if there is any, okay, if I have this and this is 1, it will output 1, and no matter what's the threshold, the output will just be 1. Maybe let's do an example with this. So let's do this example. So if I have like an inhibitory edge like this, and I have threshold equal to 1, okay? So these are the inputs. If x1 is equal to 1, it will shut down the machine. So there is no sum, and this is 0. If x is again, x1 is again equal to 1, this will shut down, and I will have 0. And just in this case, I do the sum, because this is 0. So the way the inhibitory edge works is that it behaves like a normal thing if the input is 0. If the input is 1, you will have 0 in the end. You skip this step, basically. Okay. In this case, you get 1 and 0. And so you just get 1. You get this. So what does this represent now? Anybody? No? Yes? So it's like not x1 and x2. Okay. I just want x2 basically. I want to select x2. So I shut this down. So we call this thing also a decoder. So something that a decoder for the vector 0, 1 in 0, 1 square. So it's basically a McCulloch-Pitts unit that selects. It will be true only on one single vector. Yeah, I know this word means something different in different contexts. In this context, it means this. We're gonna have a look at that later on too. So can we do this with many variables? Yes. No. Should I do it or so? Like you can do basically ands and ors that were the ones without the inhibitors. So if you just have this type of edges, how much you can do? This is the question. Like, can you do all the Boolean functions using just ands and ors and these machines? So I don't know. Does someone have an idea on how? I'm not gonna write the truth table because it's gonna become too big. But can like if I do this. With 3. So we want to find a way, like, if I put theta equal to 3, what does this represent? We can write the table. Okay. So we always calculate the sum. And I can wait.
You have a one when all three of the variables are one.
Yes. So it's like x1 and x2 and x3. And more in general, if you have like if you have x1, xn, and you put n as the threshold, you will get x1. So you can do the same thing but with many variables. That's the idea. And analogously, like if you want to do or of many variables, you just put 1. Or among many. So the question is, we can do all this with just the normal arrows. Why do we need the weird arrow that I introduced? Like, can we do any Boolean possible function just using the classic arrows that just transfer the input? Since we can do all this, I mean, why not? But there are some we cannot do. That's why. But so, yeah, I mean, let's try to stick to what we have. Imagine that we don't have the weird arrows. The question is now, what can we do? So the answer is, I mean, I'm not asking you these questions because, like, yeah, it's a bit bad. But yeah, so we can do a monotonic logical function, meaning that, what are the monotonic logical functions? If you have a monotonic function, normally in maths, is like, for example, strictly increasing or strictly decreasing. So it's a function f. So the result of this proposition is that there is this category of Boolean functions that can be done just using these arrows and the thresholds, okay? So we say that a logical function is monotonic if given two inputs and one is smaller. I mean, with the classic function was like f is said to be monotonically increasing. If I have two points in the domain, one is smaller than the other, then the function will be smaller. Monotonically increasing, okay? But just that here in the domain, our domain is 0 to, like here in our case, x and y belong to 0, 1 to the power of n. So the question is, what does it mean being smaller than another if you have these vectors? It's not clear what is the notion of order. So you have to define a notion of order in the domain in order to be able to talk about monotonicity, okay? What does this mean? Like when the points are vectors. So, oh God, no, let's call this W because I called Y the output and I'm not crazy. So. Is everything all right until now? Yes. Is everything too easy also? Okay. Or too hard, like it's okay. So if I get 2 points belonging to the domain, meaning belonging to this, so I have x that is equal to x1 dot x n, and w that is w1 wn. Okay. How can I say that one is smaller than the other? So let me do the same I did here. Okay, now here I put y. I should put w in the slides. Yeah, but so what if I want to say that x is smaller or equal than w? I say that the number of ones contained in x is contained in the number of the ones contained in w. So for example, if I have this 0, 1, 0, I say that this is smaller than 1, 1, 0. Like in the same position, this like whenever this has a, so this is smaller than this is smaller than this, like for each entry basically, okay. Or this, so I don't know. Is it that clear? Should I repeat?
Yes.
Okay, so this is greater than this is greater than this, and this is greater than this. The greater or equal. So I do it for each coordinate, basically. I take two vectors, the one that is bigger and the one that is big for every coordinate. There are some that you cannot compare, okay? Because imagine that one has a bigger coordinate. So for example, if I take this, if I take this vector, I don't know what's the relation between these two. But if one is, so the definition of monotonicity is that if one is smaller than the other, then f of this one, then if x is smaller or equal than w, then f of x. That is just a number because the image is 0, 1. Would be smaller or equal than f of w. So this condition must be satisfied, but know that there are couples that I cannot compare because this I don't know if this is greater than this because for this coordinate it is and for this coordinate it is not. So there are some vectors I cannot compare. But the thing is that if I can compare them, then this is true. Okay. So the proposition that I'm not gonna prove, but I'm just giving you the idea of why this is true, is that uninhibited threshold elements of McCulloch-Pitts type can implement monotonic logical functions. So Monotonic logical functions are functions that have this property, okay, that I just explained. But I can do those with the uninhibited threshold elements of the McCulloch-Pitts units. What does it mean? With like units that have just the normal flashes, like this, sorry, these arrows. So if I have a McCulloch-Pitts unit that has only this, I can do all the Boolean functions that have this property. So here we add the end at some point. Let me let's have a look at the end and the or we did before. So we just do what it's the same thing. So let's put directly the result. So this was. Let's do before the end. So when I do an AND between 2 points, 2 variables, the AND is like what I want to say is and or operations are monotonic. So satisfy that property. Why? Because I mean this is greater than everyone else, right? Because if I compare this couple to all the other couples, this 1 is greater than the others, okay? And f of this is greater than the others. So this property is satisfied for the AND. So ANDs are monotonic. If you do the same for the OR operation, so this is again monotonic. Because these two I cannot compare, okay? So I don't compare them. But if I take this and I compare to this, f of this is bigger than this is f of this. I don't know, we can write it as 1. And is monotonic, and also OR is monotonic because it satisfies this property that the image of things that are one smaller than the other is one smaller than the other. Is that clear? Okay, so if I do combinations of, this is true also for like higher, for n variables, I can do the same. So what happens if I combine ANDs and OR? This property stays the same, like compositions of monotonic, this stays monotonic. So whatever type of network that I can construct, okay, I showed just one neuron, but I can actually stack them. I can do many layers. I can take as inputs the output of the previous one because the outputs Y are always 0 and 1. So I can take those as inputs. So if I stack those type of operations and I compose them, what I obtain is still something that is monotonic, so that preserves this property. So, but this set of monotonic function is a subset of all the Boolean functions. So I cannot do everything just with the normal arrows. That's the point. So using just like excitatory edges and using what we call this uninhibited threshold McCulloch-Pitts units, so the one that don't have this inhibition edge anywhere, are the ones that just can cover all the space of like the monotonic logical function of all of them. Are there any questions so far?
Wait, take a break.
Yeah.
Now with
Do you want to take a break of 5 minutes? Yes or no? How many for yes? Let's take a break. I'll see you in 5 minutes.
We're back. You can.
Yeah, I think we start back, and I suppose we will survive until the end. So until now, we're just seeing that if we do networks just using excitatory edges, we can only do monotonic logical functions. Basically. That's what this proposition said. If you want to have a look at the proof, it's on the Rojas book. So if you want to, I don't know, if you're interested in detail, or everything actually is on the Rojas book. There's more than what I said. So if you're interested in further details, there's like the link on the book is like, I think it's called NN on the Moodle, and you click and you have the book and everything is
You
there.
want to use the microphone much closer.
Yeah.
Yeah, that's there.
And yes, so that's the book. The idea of the proof in general is the fact that you can do these uninhibited networks by composing, it's like ANDs and ORs, and then all the ANDs and ORs kind of preserve monotonicity. So whatever you will obtain will have this property of preserving the order that is in the domain. That is not like a total order, because as I said, there are vectors you cannot compare, like this one and this one, you don't know which one is bigger than the other, so you don't compare them. Just compare the ones that you know that are one bigger than the others. And so if there is one that is smaller than the other, then the image will be smaller. Yeah, so now, what are these? These are the ones with the neutralizing input, like this inhibitory edge. What does the edge do? As I said, it shuts down the neuron if it gets input as 1. And if it has 0, it just passes 0 like the other one. So if it passes 0, and if there is none of them that is 1, none of those weird ones that is 1, the network will compute the sum of all of these, and it will sum 0 whenever you have a weird edge. And so in the end, what you will obtain is the sum, and you calculate the activation function over the sum. So this, the activation function of threshold theta. I think we did already the first example that was, or we did the inverse. Maybe we did the inverse, but yes, this one is x1 and not x2. So it's selecting x1 basically with threshold 1. If I output threshold 2, it will just output 0, okay? Can we do these other two? What are those other two? Like, we're trying to understand why putting this inhibitor is important or not in the network. So maybe I can write this down. Oh, so the thresholds can be 0, because I said that the threshold belongs to the natural numbers. There is some mathematicians who don't believe in that. I do, so I don't write n united to the element 0, 0 belongs to n. But yeah, it's unrelated to this course, so let's move on. But the threshold can be 0. So what is going on here? So this is the sum and this is the output. Here, both of them are activated, so the sum shuts down. There is no sum, like both the inhibitory edges are activated, so the output is 0. Again, the output is 0 because 1 is activated, the output is 0. Here, the neuron is not shut down, but the sum is equal to 0 and passes the threshold that is 0, so I get 1. So what is the operation here?
Oh,
Yes, no. And I don't know. Does someone wants to say what's the last one? Or I write the table with just 2 lines. I write the table with just 2 lines. X1 can be 1 or 0. This is the sum of one element, and this is the output y. So when x1 is equal to 1, this is the network that is. So if this is equal to 1, the thing shuts down and it outputs 0. That's how the inhibitory edges work. And what happens here is that I have 0, so I calculate the sum because it just passes. And the threshold is 0, so I get 1. So if I compare this to this, what is the operation that I'm doing on x1? Yes, not x1, x1. Great. So the question is, are these examples monotonic? For example, let's have a look at this. I have this one that is smaller than everyone, right? So 0, 0, for example, is smaller than, I don't know, this 1, 0, 1. Right? Because this is smaller than this and this is smaller than this. But f of this, I don't know. I don't want to write it, but yeah, f is 0, 0 is greater than f is 0, 1 of 0, 1, right? Because this is equal to 1 and this is equal to 0. So it's not monotone. So basically, whenever you add something like this, what happens is that you break monotonicity. And I mean, by monotonicity here, we mean increasing monotone. I don't know why I didn't put the word increasing, but it's like the inequalities are in the same stance between the domain and the image. So, yeah, this is like what is called with all this, we can do what is called the universality property of McCulloch-Pitts networks. So we cannot do much with these networks, and someone has an idea of why we cannot. Like, we cannot do fancy stuff with this. We can, at some point, you stop. And not because of the presence of these weird arrows, or because of the fact that the activation function is very simple, like it's the step function, but because of someone has an idea. So what this proposition says that we're gonna show soon is that we can do all the Boolean functions. So we cannot do all the functions with these machines. We can just do the ones that go from 0, 1 at the power of n to 0, 1. Whereas, I don't know, in machine learning in general, people are interested in like approximating fancy functions, like actual functions that, I don't know, do more complicated tasks. So the secret in all this is that the weights here are set to 1. So they're either passing or either they're shutting down. But the weights, like there is no number. You've seen in the first week that you were putting numbers, like weights, like on the edges, right? And here, every weight is 1. So the problem, the limitation probably of this type of machine is due to the presence of unit weights. But anyways, we can do many things. Among those, approximate any function f. And not just with the ones with like normal arrows. We need those shutting down ones. So I'm not gonna make the full proof. There is 2 ways of doing it, okay? One way uses the so-called disjunctive normal form. So I'm gonna write it down if you wanna Google it and like have a look at that. That is not the way I'm gonna prove it, but it is like a very nice way of proving this result. I mean, by every Boolean function, I mean, really, I decide the function f that goes from 0, 1 to the power of n to 0, 1. And for every n uplet, I decide whether this is mapped in 0 or 1. So the thing that we're claiming is that any function of this type can be written as a McCulloch-Pitts network of 2 layers. So it's not that you do it infinite, like you actually don't need more than 2 layers, okay? That's the result. Why do we need this? How do we do that? Let's okay, an elegant way of doing that is to use the disjunctive. So the disjunctive normal form is a way of writing any logical expression, any logical function as a or of ands. So you have blocks of ands and negations inside, and ors, like the big, in the big picture you have ors, and then you have parentheses of ands. Kind of. This is the idea of this normal form. So when you have that, you can put in the first layer all the blocks of ands and negations, because you can do negation, as I said, putting a circle, and you put the ands as because we know how to do the ands, like we just put the general and that I was telling you before is this. So you have x1 dot xn. You put treasured n. You put treasured equal to n, and you have an end. If you want to put some not, you put a circle, and it works like as a block of ends. This is the first layer. And then in the second layer, you put, since it is an OR of ends, you put in OR all this. So imagine that you have a so imagine that your normal form is this way. This is OR, something, OR, okay? That's what that result said, and it tells you how, given whatever expression, to write it in this way. Imagine that you can write it in this way, then each block corresponds to something like that, either with circles if you want to put knots, because there might be ands and not in these machines. Okay. So for each of these parentheses, you do a block like that. Here you do another one, etc. And then with all this, you put them in an OR, because we know how to do an OR. That is the second layer. So this is the first layer that takes care of all the parentheses together, and the second layer just does an OR. You put normal arrows everywhere, and it does the OR, the global OR. Because I told you that x1, xn, this is the result from before. We knew that this corresponds to the equivalent to x1 or etc. or xn. So the difficulty, if you want to have a look at this proof, is how to write any expression in this form. But whenever you have this form, we can use what we already know to write a network of 2 layers that uses that form. You can have a look at this on the internet probably because it's not on the Rogers book, but I'm gonna do the proof that Rogers did. Gonna do, like show the idea. But yeah. Are there any questions so far? Is everything all right? Okay. So, let me cancel this thing. Okay, the proof that Rogers does is not the one that gives you the smallest network. It might be redundant, but it does the job. So given any function gives you a network that does the same thing. So it's okay. Let's show you. Okay, to do the proof, we have to use these things that are called decoders. I showed you before already one. I think it was this. I'm not sure, but I think it was this. And I put threshold as equal to 1. So this was the decoder for the vector 1, 0. Because this comes out equal to 1, so f of everything is 0 except for f in this point that is equal to 1. So if you want to write a table for this function, it is x1, x2, f of x1, x2 is so from this example, what we want to learn is that if I this concept is needed for the proof, that's why. So this type of network is equal to selects basically an input. So given an input, I have a way of writing one neuron, just one neuron, that is equal to 1 just on the vector that I want, okay? And the way I do it, and this is also true for like bigger actually networks, especially for the ones that I showed there. So this was for the vector 1, 0, but the ones that I showed on the slides, maybe I can, let me write them down. Okay, so imagine that I have 3 inputs, like x1, x2, x3. And I want to find a decoder for the vector. Let's do the same as in the slide. So it's 1, 0, 1. What I do is that I put the inhibitor where I want to have 0, and I put the excitator where I want to have 1. And as a threshold, I put how many 1s I have. 2. I can show you that this network is, that we're gonna do the table, but this network does what I want. So it's equal to 1 on this vector, and it's equal to 0 everywhere else. Everywhere else in 0, 1 at the power of 3. So in all the points of that cube is equal to 0 except on this one that I want. So I want to find a way of selecting vectors and say, okay, these are like, I want to describe my function as, for these vectors, you have to be true, the rest you have to be false. So if I have a way of picking vectors and saying you have to be one in this, the image of this should be one, then I can put all these in the first layers, basically. I want the first layers to be all the true ones, and then I put them in OR, because OR I know how to do it. And then I have two-layered networks, and that's my result. And I need those things to say not this coordinate in this construction, right? But let's see why this is true. Do you think that this is true? Yeah. What a remaining table with all the numbers. So what is going on? Where is the sum and where is the threshold of the sum if there is any? Because I don't know, sometimes the thing shuts down. So I said, here I have the inhibitor edge. So whenever x2 is equal to 1, this will shut down the machine. So x2 is equal to 1 many times. So it's here, 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 and here. Rest of the time I'm gonna do the sum. So the sum here is 2. The sum here is 1. The sum here is 1, and the sum here is 0. And then I let the path, I mean, here the thing has been shut down, so the output is 0. 0, 0. Because whenever the machine has been shut down by an inhibitor, the output is 0. Then here it passes, so I say 1. Here it doesn't pass because it's 1 and my threshold is 2, so it's 0. Here I add no sum, 0. Here I have 1 and it's 0, 0. So this thing does what I want. Because it's equal to 1 just on the vector that I want. And so the second example you can see on the slides is similar, kind of. Let me write it on. And this holds also for like 4 axes. So you just do the sum basically of the ones as a threshold. You put inhibitor wherever you have a 0, and you put an excitator wherever you have a 1. Yeah. So you have to pay attention to the threshold, because if the threshold was smaller, for example, if the threshold was 1, and that is not the number of ones that is in this vector, what I would have obtained is that also this would have been 1, also this would have been 1. So this is not what I wanted. I would have gotten something that fires also for other vectors that are not my target anymore. So let me write as well the other examples. I don't know if it's really useful, but yeah. In this case, you shut down everything except for this one. And with this network, basically I target the vector 0, 0, 1. Is that clear? Are there any questions? Okay. Pay attention to the threshold whenever you build a network like this, because it's in the exercise. So how do we prove this result? So whenever I have a function, imagine that the function goes from 0, 1 at the power of 3, 2, 0, 1. I can specify the values of the function over all the points of the domain because everything is discrete. And that's why in the beginning I don't did those exercises that were pretty bad, but like they were about knowing that the domain is finite. So I can tell for everyone what is the image, like in a very like straightforward way, because I can write all the domain in a list. So whenever the function is specified, basically I'm deciding whether to put this is the specification of the function in some sense is like a list of zeros and ones that is here, right? Well, where am I sending all those galaxies? And so I want to know which is the indexes in which I'm sending people to 1 or to 0. And I choose the ones that where there is 1. Imagine that I have 1 here and 1 here, and all the rest is 0, okay? So I know that there are some vectors, this one and this one, for example, that need to be sent to 1. And the rest should be sent to 0. So there is like this, I don't know. I call O the subset of F of 0 and 1 at the power of n. That is the set of the vectors that should be sent to 1. So that's for every element x that belongs to O, it holds that F of x is equal to 1. So for each of those, I built a network, like a decoder for that vector. So the way I'm gonna construct this thing is that I do something for the first vector, something for the second, etc. And this is the first layer. Okay, each of these first layer things will give me 1 if the vector is the one that gives 1, or 0 otherwise. And then I put them in OR. The second layer is just an OR. So it's threshold equal to 1, or of all those things. And yes, this is the network that does what the function will do. There might be some repetitions in this, like it's not the smartest like network to do given a function, but it is a network associated to a function. So that's all like proves the result. Are there any questions? So how much time do we have? Not much.
With the break taken into account, it's 10 minutes.
Okay. So this is an example. You can see it on the slide. So like it's an actual network that does what I was saying before. So those two are actually 2 decoders for the function is specified in that way. So you have input vectors, all the others need to be 0, and those are the 2 that I want to be 1. And I construct the function in that way. So I do a first layer of decoders for each vector that is sent to 1, and then I do an OR of all of those, and that does the job. And I think this type of like function cannot be written as the one with all in the normal arrows, like without using the circles. I don't think this is possible, or I don't think this is possible in 2 layers. So that's the constraint. So yeah, I think the bad things are gone, and this is a cool thing that I wanted to show in the end. Thank God. This is the as I was saying, this is 0, 1 to the power of 3. And one can say that having a threshold, so imagine that we are using just, forget again about these arrows. Let's just consider these ones, okay? Let's recap what was the OR operation. So you have x1, xn. This was the OR. And since there is no inhibitory edge, the sum, when I compute the sum in that table, so what I do is that I write x1, x2. I write all the possibilities, xn, whatever. So I write x1, all the possibilities xn. Then I do the sum, right? And then I do the step function of the sum. And here, this is never a bar, like it's always computed because the neuron is never shut down, like you always have like nice arrows, okay? Imagine that, so the sum is the sum, I that goes from 1 to n of x. So, what is putting a threshold doing on the space of the possibilities 0, 1 to the power of n? Like, let's do it with n equal to 3 because I don't like drawing hypercubes is not really the thing one wants to do. But yeah. So imagine you're in the space where you have just x1, x3. So the sum is x1 plus x2 plus x3. Should I write bigger? Yes. When you're checking for the threshold, what you do is that you're asking yourself whether the sum is greater than theta or not. That's what the Heaviside function is doing. I don't know, should I go back to the slide with the Heaviside function? Do you believe me? This one. So this activation function is like, are you asking whether x1 plus x2 plus x3, that is equal to a number, that is s, is greater or equal than the theta number? So what do these equations mean in the cube? That's why I was drawing a cube before, so that's me. Okay. So this is an equation of a plane. I don't know if you believe me, but like when you are in R3, the hyperplane is given by one equation, and the straight line is given by two equations because you're intersecting two planes, and here you just have one equation. In the same way as you have straight lines on R2 that are given just by one equation. Okay? And in R3, there is this thing that you consider the coefficients that are put before your variables. So you are in R3, okay? Imagine that we are in R3 and not in 0, 1 at the power of 3. Imagine that this is x1, this is x2, this is x3. So the coefficients that multiply the three variables are the direction of the normal vector to the plane. So in this case, the normal vector is the one that is perfectly like distant to all the three. It's the diagonal of the cube if you want. There's a better cube there. But yeah, so, and also those, if you remember the first class, the weights were multiplying the inputs. And here, the fact that we're using unit weights, so we are not using weights, we're just like letting things pass as in the OR, means that we'll always have planes that are in that direction. So the direction is somehow fixed because I cannot multiply by stuff here, okay? So I said that I was having OR for theta equal to 1. Okay. Theta equal to 1 means OR, and theta equal to n means and between all of them, right? So, so in this case, it would be 3. So those hyperplanes, so the plane where the result changes is this one for the OR. Because so equal to theta means that if you're so having an inequality, okay, having an equality, so having the equal theta will mean having a plane. So in the OR case, you have a plane equal, this equation equal to 1. And the OR is like positive if you're greater or equal than 1. So the height, basically the slice of your cube that is towards you in this case would be 1, and the rest will be 0, okay? So kind of the threshold puts divides in some way your domain. So the pre-image of 0 and 1 in the image space of the function f divide the domain into two regions, the ones that are sent to 1 and the ones that are sent to 0, okay? The ones that are sent to 1 are the ones that is the slice of the cube towards you, including the plane, and the ones that are sent to 0 are the ones that are down. But the case in which this is equal to 3, if we were in R3, we will have no problem. We will have a plane that is translated in this direction and is placed at distance 3 from the origin, no, not 3, but yeah, right. What happens, is not distance 3, that intersects the axis at height 3. But since we have a cube and we are not in R3, what happens for the end? So this is the OR, because theta that determines your hyperplane is the one. But what happens when we have the end? So we have theta equal to 3. We have this hyperplane that intersects the axis at height 3. So imagine to continue the x1, x2. The plane that I'm talking about intersects the axis at height 3. So on the cube, the cube is sliced if you want, but how it is sliced for the case of the end? Anyone? Yes, just 1 point. So basically you got just this point here. Yes. And yeah, here they draw a picture as well for the case of equal to 2. But the case equal to 2, I recall you that for the case of 3 variables does not correspond to the end. So that is the idea, if you want to visualize a little bit this thing. And all the planes will be parallel to those ones. Because as I said, I cannot move the plane, because moving the plane would mean adding coefficients in front of the variables, and I can't because my weights are all equal to 1. Right? So being able to modify the plane is not possible. Yeah, I think that's all. Are there any questions about this cube thing or about the rest that were treated today? Okay, I think that's all then. And I'll see you on Friday. And don't forget, there will be a poll to choose whether you want to do lesson on Friday or on Wednesday. Switch with it.
And something from me, whether it's going to be on Friday or Wednesday, the exercise session, basically the idea is that you can do the exercises whenever you want. The exercise session is not mandatory, but during the time, whichever it will be, I will be there in the room and you can come and ask me questions, or you can just stay in the room and do the exercises if that's more comfortable for you. But also feel free to like email me or them if you want to have any questions answered. So that's it. Yeah, thank you from both of us and have a good day.